Okay, so my name is Nasniewski, and we're doing this monoidal category theory. We're up to chapter 4. Chapter 4 is relationships between two categories, and we already had functors, we had natural transformations, we talked about equivalence of categories, and now we go section 4.4, which is about adjunctions. So adjunctions is probably the first hard concept, or the first real concept in category theory, and it's arguably the most important concept in category theory. Okay, it's very important, and we're going to spend a lot of time talking about it. It shows up all over, and I'll explain why, and I'm going to introduce it in 4 different ways, okay? Now, but one of the ways we can do it is as follows. We've seen this diagram before. You have category A, B, you have functors F and G, you have the identity here, you have the identity here, and you have F composed G, G composed F, whatever, over here, okay? And so the first time we saw this in terms of categories, we saw it in terms of sets before, but the first time we saw it in terms of categories, we said this was an equal, and this was equal. When these two are equal, in other words, F and G are inverse of each other, so then we have this isomorphism of categories. So A and B are isomorphic categories, okay? That's what an isomorphism of categories was. Then we weakened this, and we talked about, no, they're not equal, but they're isomorphic, okay? And in that case, we have A and B are equivalence of are equivalent categories, and this is an equivalence of categories. And F and G are no more inverses of each other, they're quasi-inverses. Okay, great. So we've progressed. We've weakened this notion from equal to isomorphism. Now we want to go one step further. And the step further is, instead of talking about there being an iso-natural transformation, a natural transformation there that's isomorphic, what we're going to do is we're going to say there's a natural transformation like that. Okay? And we're going to call this Greek letter eta, eta, okay? And the same thing here, we're going to have a natural transformation like this. Okay? And it's called, I'm sorry, so let's write this. This is called the unit. This is called the co-unit, and it's called epsilon. Okay, and so this is pretty standard. Okay, now we don't just want these two things to exist; they have to satisfy some other requirement, and the other requirement is called the triangle identity. Okay, but hold on, before we do that. This is the first time that directionality matters. In other words, this arrow is going this way, this arrow is going this way. So what we're going to do is we're going to have these functors. They're going to be these functors. I don't want to call them F and G, although you can call them whatever you want. I want to call them left and right. Okay, so I'm sorry, I had an F here. I'm going to cross it out. I'm going to make it a left. I'm going to cross this out and make it a right. I'm going to cross this out, and I'm going to say, what is this? First do right, then do left. So this is right, composed left. And this is, cross this out, this is start here, do the left, and then the right. So this is left, composed right. Okay? So again, it doesn't make a difference. You can call your functors whatever you want, but it's going to be easier if we call this left and right. Okay? Now, these two, the unit and the co-unit, have to satisfy some higher condition, some higher axiom, and the axiom shows how they relate with the functors. And so it goes as follows. Take the functor R. Okay? I'm now going to describe a natural transformation from R to R, L, R. Okay, so that's from this functor going like this to this functor going like that. Okay, and this is nu at the R thing. So I'm sorry, this is eta. So that's eta at the R. So let's just go through this. Eta goes from the identity to R. What happens if we don't first do the R first? So we do get this. So then we have this, hold on, and this as R eta, epsilon. This goes to R. Sorry, don't want double R. Double R means the real numbers. This is the functor R. Okay, and this is just equal to each other. Okay, in other words, we have some requirement on how these functors and natural transformations interact. This is one of the triangle requirements, and then there's another one. Okay. Main point. This goes to L cross R. This goes from L cross R down to identity. So this goes up, this goes down. This goes up, this goes down. Okay. Okay. What this means and how it works, that we don't need to see now. Maybe we'll talk about it later, but we don't need to see this. Okay. So what we have for this is the first definition of what an adjunction means, okay? An adjunction is when there's a functor this way and a functor this way and a natural transformation this way and a natural transformation this way, not an isomorphism, main point. Eta and epsilon are not isomorphisms. If it was, then we'd have a special type of adjunction called an equivalence of categories. We're not dealing with that. They're just morphisms, such that this commutes and this commutes. That's the first definition. That's pretty opaque, okay? What does it really mean? It's not clear from here what it really means, okay? But what we can say is it's a weakening of equivalence of categories, okay? And this is something that we saw a few times, namely, whenever you have a notion, if you weaken it, it becomes more applicable. It becomes more, you can use it more because it shows up more. Okay, great. I want to write the way we're going to say this in 5 different ways, 6 different ways. Ready? Okay, we're going to say L and R form an adjunction. Okay, or they're adjoint functors, okay, and we say as follows. L is, again, here the direction matters, okay, so we're going to have that. We didn't care when we were talking about equivalence of which way was one way and which way was the other way, because they're both isomorphisms, so we didn't really care, but here we do care, okay, and we say F is left adjoint to R. Okay, another way of saying that is R is right adjoint to L. Okay, and now we're going to describe it with symbols. We do it as follows. Ready? L dash R. Okay, so here's a symbol. Sometimes it's called turnstile, and what it means is it's pointing to the left adjoint. Obviously, not all the times will this be called L and R. Sometimes they'll be called F and G. Sometimes they'll be called, most of the times they're not called L and R, but we want to show it. So basically, the turnstile points to the left adjoint, and so we can write the same thing in one dimension as this. Okay, and finally, the last way we write it is like this. Here's category A, here's category B, here's left, here's right. And the way we write that there is an adjunction or these are adjoint functors is the same thing. That turnstile is pointing to the left adjoint. Okay, so what we're going to do now is, this is one definition of it, pretty not clear what's going on, but it's not, and then we're going to see 3 more definitions of what's going on, and then we're going to go through a ton of examples, and it'll all come up in the examples. So this is called definition 1. Let's erase it. Okay, and for all the definitions are equivalent to each other. We'll talk about that later. And whenever we have one or all of the definitions satisfying these equations, well, if you have one, then you have all. If you have all, then you have one. If you, whenever we have that relationship, what we're going to say is that they're adjoint functors. Okay, let's look at another way of saying it. Okay, it goes as follows. This is definition 2. You have A, you have B. Okay, you have left, you have right. Okay, let's just put that in. Okay, and what we're going to do here is we're going to write it like this. And what an adjunction means is that in the B category, okay, we can look at a typical guy A. A is in here, L of A is in B. Okay, and we can look at a typical guy B. So let's go through this. A is in A, B is in B, L of A is in B, and you have that, and B is in B. Okay. On the other hand, here's another thing you can do. You could look at the Ham category of A, okay, and you can look at A and right of B. Okay. And what we want to say is these two Ham sets are naturally isomorphic. We talked about natural before, and I'll go through the details of what that means in terms of nature. What that means is that if you have A and an A prime, they satisfy. If you have B and a B prime and you have a function between them, a map between them, so then you're going to get a different box and it satisfies this. But basically what this says is not that the Ham sets are isomorphic. Okay, you kind of had that with equivalence of categories where you had full, faithful, and essentially surjective. Full, faithful means the Ham sets are kind of isomorphic. Okay, but there is a relationship between the Ham sets. That's the main point. Okay, let me just write this another way. Okay, and basically the way to write this is A goes to R of sorry, let's write it here. Here you have A goes to R of B. Okay. For every map like that, there's going to be a map from L of A to B. Okay. But hold on. I just want to show you where you go. I just want to show you where you go to get this, how this definition is related to that previous definition. So what I'm going to do here is I'm going to take this map and I'm going to apply L here. So look what we get. L of A goes to L of R of B. Okay, no problem there. Okay, but now I want to take the co-unit of this. So what's the co-unit? It takes the left and the right of B and it goes to B. So we're going to write this as the co-unit. The co-unit is written as epsilon. So here's F, here's L of F, and we compose that with this. Notice what we just did. We started out with a map from A to RB, and look what we get. We get a map from LA to B, which is exactly that. Okay, so by the way, this is B. So what we did was I showed you how to use this co-unit to get this. Okay, great. Let me just show you the other way from here. Okay, you have a map from L of A to B. Okay, I'm sorry, let me be more careful. What I showed you was if you have a unit and co-unit, you get this kind of isomorphism. Hold on. You get a map from here to here. Good. Let's do it with this side. Okay, I'm going to take L of A to B. I'm going to apply R to both sides. Okay. Okay, look what we have here. R of L of A. Now watch what I do. Take A, an element there. Okay, and so that's the unit at A. And that's, I don't know, we'll call this G. And so we'll call this R of G. And look what we have when we compose this, A to R of B. So again, what did I use? I used this unit to go from here to here. Okay. Now, those triangle identities, that corresponds to saying that this is really an isomorphism, okay? The fact that the triangle identities are made out of natural transformations, so this is natural and this is natural, and these are functors, so it works very nicely. But again, what it says is that going from here to here, they're really isomorphism. It's not just that you get from given one of these guys, you get one of these guys, but they're isomorphics. In other words, given one of these guys, follow this routine, you get one of these guys, follow this routine, you get back the same thing. So that's what that triangle identity shows you. Okay, great. Okay, now this definition is going to be the one that's used the most. This definition is going to be the one that's used the most. But again, all four definitions are equal to each other. Main point, okay, that unit and co-unit, if you have that unit and co-unit, you have this isomorphism of Ham sets. Great, let's go to another definition. Okay, and it goes as follows. So this is definition 3. So it says as follows. When do you have an adjunction? Oh, when you have a map from A to L of R, I'm sorry, R, so R of L of A. Okay, so we call this the unit on A. So when you have a natural transformation like this, now here's what I'm doing. I'm bringing in this unit. Okay, so again, the first definition said you have a unit and a co-unit. The second definition said you have this equivalence of Ham set, you have this isomorphism of Ham sets. The third definition is you have this unit. Hold on. Okay, okay. And what this says, this has a universal property. What's the universal property? So A goes to R of L of A. Okay, now if you have any other map that goes, A goes to not R of L of A, but R of B, hold on, then there's a unique map. So for any map here, there's a unique map, L of A to B, such that, okay, so I'm sorry, given this, I want to show you why this map is special. So it says as follows. This map is special because for any map like this, in other words, it's the best fitting thing, for any map like this, there is a map from this. Okay, so let's call this F, and let's call this G. Okay, for any map F, there is a map G such that R of G, which goes from here to here. Okay, so let's do that. G goes from L of A to B, R of G goes from R of L of A to R of B, such that this commutes. Okay, so that's the definition of this unit. It's a special map from A to R of L of A, okay, that satisfies this requirement. For any map like this, there is a map like this, such that when you do R of it, so let's do it like this, when you do R of it, this triangle commutes. Okay. Okay, main thing. Notice what we have here. We have this equivalence between, we have this equivalence between Ham sets from A to R of B, L of A to B. Okay, that's exactly definition 2. So this is kind of a marriage of definition 1 and definition 2. It uses the unit and composes with that in order to get, uses the unit, composes with this to get that. Okay, guess what? So this is definition 3. The definition 4 is exactly like that. Okay, let's just do it. It goes as follows. L of R of B goes to B. This is a co-unit at B, okay? And it also has universal property, okay? And the universal property is that if you have any other R of A to here, Nope. Nope. I'm sorry. If you have any other L of A, right? L of A over here, okay? Then there is a morphism from R of B to A, such that when you apply L to this, you're going to get, so this is F, so this is L of F, and this is G, let's say. Okay, and so you're going to get something like this. L of R of B goes to L of A. Then this commutes. So this is definition 3. This is definition 4. Okay, main point. This uses the co-unit as the main thing, and it shows you how to get that equivalent, that isomorphism of Hom sets. Here's one set, here's another set. You get that isomorphism from this. Okay, and again, the universal property corresponds to that triangle identity. Okay, so that gives you all 4 definitions. Okay, that gives you 4 definitions, and it's very nice. In the book, I go through all 4 definitions, and I show how they're all equal to each other. Okay, in other words, if you have an adjunction because of definition 1, then you have an adjunction because of definition 2, 3, and 4, etc., etc. It's a very technical proof because you have to constantly keep in mind, keep track of what you're doing and what you're composing with. I don't want to do it in the video because it's just a pain in the neck. You have to just follow the book very, very carefully. Main point, okay? There is some type of relationship between L of R, between the unit and the co-unit and the left thing and the right thing. Okay, great. Okay, like I said, the rest of the section is just example after example after example. That's a good thing. We like that. We're going to be bored of examples. We're going to see them all over, and we're going to get a feel for what adjoint functors are all about. Okay, great. So first example is the simplest example, and it goes as follows. You ready? Let's just remember what we did. Take the one object category. So this is the one object category, okay, with one identity morphism. Okay, what we saw before was, here's the 2, I think I did 2 of I, and this is the 2 object category. Let's call it A and B. Did I call it A and B? I don't want to call it A and B. I just want to call it 2 object category. You know what? I want to call it S and T. Again, you can call objects anything you want to call them. So let's call them S for source, T for target. Okay, and this is an isomorphism. And one of the things we saw in last section, this is an equivalence of categories. Okay, namely, this goes here. Let's just go through this. You ready? This goes here. Okay, this whole thing collapses down to the single point. There's nothing else it can go to. Okay, so that's not interesting. Okay, but the main point is this functor is, there's an identity between every 2 morphisms, and the main thing is, even though this goes here, but still it's essentially isomorphic. So yes, there's nothing that hitting the T, but it's essentially isomorphic. Okay, great. Now, what I want to do is I want to weaken this notion and talk about this, the one object category, star, and the category 2 with just 2 objects called S and T, but they're not isomorphism. Okay, main point, it's not an isomorphism. So this is a different category than this. This is the category with an isomorphism in between them. This is a category without an isomorphism in between them, just a regular morphism. Okay, great. Let's just do it in terms of the Hom sets. Okay, so what are we going to do? I'm going to describe 2 functors between these 2 things. Okay, this one is easy. I'm going to call that one, I'm not going to call that one star, that would be stupid. I'm going to call that one exponentiation, like that. Because there's only a unique map from here to here. Map everything into that dot. That's it, finished. There's one map that does that. Okay, as opposed to that, I'm going to call this left. Okay, let me show you how this works. So ham of 1 is going to take star. I'm sorry, I shouldn't call that star. Yeah, star. The one element is star. Okay, boom of B. Okay, and that's isomorphic to ham of 2, not 2i, 2. Okay, let's do this. Of L of star, comma B. Oops. I'm sorry, I shouldn't call it B. I'm going to figure out what I'm going to call it in a minute. Okay. Okay, let's go through this. So I'm not going to call it B, I'm going to call it T for target. T. Okay. So let's go through this. Star L of T. Well, anyways, it doesn't matter. There's only one morphism. This is equal to star, and there's only one isomorph. There's one morphism here, and that's called identity on star. So this whole thing is a one object set. Okay, as opposed to this is going to be a one object set. It's going to be the morphism from this. This is going to go to S. Okay, and this, the map from S to T, is a one object set. Okay, so that's what L is. So that's very nice. That's very nice. Okay, so the map that picks out this one thing and goes to the source is a left adjoint to the unique map like that. However, hold on, because there's another map too, okay? And I'm gonna write the other map like this. I'm gonna write it like this. 1 goes to 2. This is this unique map, and then there's a map like this. Oh, I'm sorry, we should call this left adjoint. Okay, so what I just showed was this is the left adjoint. Okay, and now I'm going to make another map called R. Okay, that's very good. Guess what this does? Okay, well, it's going to do the same thing. So ham 1 star. I don't care what you want, S or T here. It doesn't matter. So we'll do this S, let's say. Well, it doesn't matter because this is going to be a one object set because S goes to the one object set. Okay, and this is isomorphic to ham of 2. Okay, right of star. That's going to go to T. That's going to go to T, comma S. We have a problem here because that's a one object set, and R of star goes to T. There is no map from T to S, so this is the empty set. I'm sorry. This R of star is T and S. Oh, so S. So that's T to S. Yeah, so that's a problem. So we have to think about that. I'm sorry, I made a mistake. What this would say is that this is on the right, and this belongs on the other side, okay? this, what we're going to get is that this is left adjunct. So this is on the, no, so we have to fix this up. Sorry, made a mistake. Everybody makes mistakes. Let's go through this. The right, so this is going to be R of something, okay? And this is going to be star of something. Okay, it doesn't matter here, but the point is this is going to be star, and this is going to be this is going to be, right, okay. So R of star is going to be this is going to be T, okay, and this, we have two options here, so let's go through them. You ready? This could be S, and this could be S. In that case, let's see. This is a one-object set, because this is a one-object set, and the map from source to target, that's going to be the single map from here to here. So this is always a one-object set. One-object set. Okay, and the map from S to T is the one object set. Or, erase, this is T, this is T, okay? So this is again a one object set, and T to R of star, well, there's only one map from here to here, and that's the identity of T. And so it works. Okay, but we can summarize this whole thing. Sorry, so you have to keep track of where your left and right is, but you can summarize this whole thing as follows. You have a map 1, you have a category 1, you have a category 2. There is a nice map here that collapses everything here. Then there's a map like this, L, and there's a map like this, R. Okay, L picks out the left morphism, R picks out the right morphism. So we get like this. Okay, so we have actually two adjunctions here, not one, two examples of adjunctions here. It's very nice. Notice also, and we're going to see this a little bit later, what this map does is it picks out the initial object of this category. What this map does is it picks out the terminal object of this category. We're going to see that later on. Okay, great. Okay, let's do another example. And the other example is as follows, and I'm going to do this fairly quickly. You have Z, the positive and negative whole numbers, and it includes into R the all real numbers, positive and negative. Well, turns out this has an adjunction like this and an adjunction like this. Okay, we can write this like this. Okay, this is called ceiling. This is called floor. Okay, let's write this out in terms of those Ham sets. So we have as follows: Ham of Z of L of R. Take a typical real number. Take a typical natural number, or I'm sorry, not a natural number because this could be negative. Take a typical whole number. This is going to be the isomorphic to Ham of R, comma, I'm just going to write this as inclusion of N. Inclusion of N. Okay? It's really N. N sits here too. N is here and N is here. Okay, look what it says. So, question, what is L of R? And this is L is equal to the ceiling. So it goes as follows. The ceiling of R is less than N. Both of these are total orders. So the ceiling of R, so let's write this like this. The ceiling of R is less than or equal to N if and only if, whoops, that's a small r, if and only if R is less than or equal to N. Main point, the ceiling of R is not a real number. I mean, it is a real number, but it sits in Z, so it's in here. Okay, so what this says is, obviously R is less than N. If R is less than N, then the ceiling of R is also less than N. So it's the number such that any number, so What's the ceiling of R? It's a number such that any number n is bigger than it, or something like that. I'm sorry, let me say that a little bit more carefully. What's the ceiling of R? It's a number such that it's not bigger than the next number. Right, that's a nice way of saying it. Okay, by the way, it's nice to look at the unit and co-unit of this thing. So let's do that. I'm going to mess up, but let's try it anyways. Let's pick R here, go here. So let's do this. Take R, take the floor of R, and then include it. Okay, and I think what that says is that's less than or equal to R. So the floor of R is less than or equal to R. Okay, let's do the other side. I think the other side, you're going to get something like this. R is less than or equal to the ceiling of R. Okay, and then you can take the unit or co-unit of this one, and basically that says n, well, I think you have both of them. N is equal to this, n, where n is a whole number, is equal to the ceiling of n, and n is equal to the floor of n. Okay, so the units and co-units actually have meaning here. Okay, so that's another example. You have to write down all the Ham sets to get a feel for this. Okay, so just to remind you, so just to restate it, the whole numbers, positive and negative, include into the real numbers, and the ceiling is a left adjoint. Okay, very nice. Okay, now this is a special case of something else. Notice Z is a partial order. Okay, in fact, it's a total order. Just think of it, it's a thin category. There's 0 or 1 morphisms between every object. There's 0 or 1 morphisms between every object, okay? Not more than that. Okay, when you have something like that, so this is a partial order, this is a partial order, and when you have adjoint functors, which are from a partial order, they have a special name. They're called Galois connections. Okay, so just to be clear, if you have a category A and B, and you have this is a right adjoint and that's a left adjoint, okay, then you have the following. So we're going to call this L. So if you look at the Ham definition of what it means to be an adjunction, it basically corresponds to the following. Well, let's just write it over here. Ham, okay, and so we have a left of little b, A, and this is little b, comma, right of A. Okay. Now, another way of saying that is left of B is less than or equal to A if and only if B is less than or equal to right of A. Okay, and so you have, just like you have a lot of adjoint functors, you have a lot of Galois connections between partial orders. They show up a lot of different places. Okay, great. Let's look at some more examples. Okay, not of Galois connections, but go back to our list of examples of adjoint functors. So go back to something we saw in chapter 1. We have a functor called L of B, okay? L of B goes from set to set, okay? And L of B is defined as for input A is a set, B is a set, okay, it's equal to A times B. Okay, now there's another functor called R of B. Okay, B is again a set, okay, and this goes from set to set, okay, and R of B on little input C is a set, is equal to ham set B comma C. Okay. Now we did this. We did these two sets. We did these two functions, and we talked about how they act in terms of morphisms way back in chapter 1. But we did them because we knew that these would be important. So let me show you in terms of adjoint functors. We have the following: L of B is left adjoint to R of B. Okay, let's see what that says. So that says as follows: ham now, these functors both go from set to set, so we're always in set. We're always in set, okay? And so what this says is L of B of A, comma, C, okay, is the same thing as A, not the same thing, but we match them up in these ham sets as ham, of A, comma, R of B of C. Okay. That's what it means to be adjoint. Of course, we have to worry about naturality, and we'll talk about that. But now let's just do this. If you're taking notes, you have to rewrite the notes, but let's just do this in terms of what these functors mean. What this says is L of B of A is A cross B. And right of B is ham okay, of B comma C. Okay, so let's just look at it one other way. A cross B to C is the same thing, or for every map like that from A cross B to C, that's a function set, then there's a map from A to ham of B comma C. Okay, and this was done in chapter 1, and it pays to go through it again. F of little a comma little b is equal to C, and what's going to correspond to that is going to be a function f prime. F prime of little a is going to be what? Well, it's going to be a function from B to C. Fine. So this is a function from B to C. So give me a typical element here. Typical element is B. Great. Well, this will equal to which element of C? Answer, f of A comma B. F of A comma B is one of those, so it's going to be like that. Okay. In computer science, it's called curring or uncurring. One way is curring, one way is uncurring. Okay, it's important to look at the co-unit of this adjunction. Okay, so let's look at the co-unit of this adjunction. Okay, okay, and the co-unit goes as follows. Okay, so the co-unit at a specific set C is a function. This is the co-unit, so it starts from ham of within set of B comma C. Okay, so this is the right adjoint. Cross. Now, what do you do with the right adjoint? You cross it with B over here. And what's the output? The identity on C, or actually the identity functor on C, so that's C. So this is going to be a map within sets from this to this, okay? Let's just see what it does. What it does is it takes a typical function f from B to C, and take a typical element b, little b, and where does it go to? It goes to f of b. So take a function and an element, it gives you the output of the function. Now this is called the evaluation function. Okay, now we have to go through what the universal property is, and I do it in the book, but basically it says this is the best fitting way of doing things. If there's another set of functions and there's another set, how do you get back to this original set? So this is the co-unit of this adjunction. Of course, you can look at the unit also. It also has meaning, but this is more famous. This evaluation function is more famous and more interesting. Great. Let's look at another example. Like I said before, the whole purpose of this chapter is show you a million examples of adjoint functors so that you get a feel for them. Okay? Okay, let A be a category. Okay, well, here's another category, 1. This is the object where there's one object in the category and one identity morphism. There is a unique functor like that. Every single object in A goes to the single object it can go to. Every single morphism in A goes to the single morphism it goes to. Nothing to talk about that. Great. Let's look at what a left adjoint would be for this. Okay, so we're going to call it L. Okay, and again, what I just want to do is I want to work out the details. Fine. Let's say that this is a left adjoint. What would that entail? What would that mean? Well, it would mean as follows. Hom, in the category of A, okay, that's here, of, take any object A, sorry. So now we're talking about the left adjoint. So L of what? Well, there's only one object here. We call it star. That's the one object in this category. Okay, and this is going to correspond to, here's a typical object here, and this has to be, this Hom set has to be the same as this. Hom of bang of A. Okay, by the way, there's only one thing there, and that's star. Okay, 2, nope, sorry. Okay, this is going to be in 1, this is going to be a star, and this is going to be bang of A. Okay, great. What's bang of A? Well, it's star. How many morphisms are there from star to star in the category 1? Answer, identity. It's a one object set, the identity on star. Very nice. Which means there's one morphism from here to here. This is isomorphic to this, so there's exactly one morphism from here to here, which means what is L star? Well, answer, very simple. It's an initial object. That's it. It's an initial object. Okay? If there's exactly one morphism from some object to any other object A, then we call it an initial object. Okay? Guess what? There's also, A might not have initial objects. Well, in that case, this functor doesn't have a left adjoint. So again, if this functor has a left adjoint, every category has this functor, but if this functor has a left adjoint, then this category has an initial object. If this category has an initial object, then this category, then this functor, then this is the thing that picks out an initial object, and of course there are many different initial objects, but the functor that picks out the initial object is the left adjoint. Okay, let's just write it for the right adjoint. Hom of A, so I'm in A now, of right star, that's a typical element of there. Okay, okay, Hom of 1, okay, and this is bang A, comma, star. Okay, so that's R. Okay, well, what's bang of A is only that. What's in this category? How many elements are there from here to here? And the answer is there's only one. It's the identity. Therefore, there's only one over here. For any A, there's a unique map. There's only one map. There's exactly one map from there to there. So what do we call R of star? Answer, it's a terminal object. And again, we can say the same thing. So turns out that the terminal object is like that. Okay, now let's just write it nicely so that we can remember it, because R and L are not interesting. So this is init for initial object, and this is term for the terminal object. And that's two different adjunctions. Very nice. It is nice to go through what the unit and the co-unit are of these things, and they're very simple. Well, this unit and the co-unit that starts here, there's only one morphism, it's the identity. But if the unit and co-unit that starts here, basically, it's that unique morphism. Okay, so take a bang of it, and then take, let's say, L of A. Okay, so this is the star, no. Yeah, so, right, so this is L, bang of A is star, L of that is the initial object, and this is A. So this is the co-unit, okay? Okay, and for this adjunction, it would be the other morphism. It would be from A to R of star of A. Bang, R star is the terminal object, so it would be the unique map from A to that. Okay, so it works out very nice. Okay, great. Next. More examples of adjunctions. What I'm trying to show is we saw all these things in chapter 3. I'm trying to show that they're all special instances of this one thing called adjoint functors. There's a hell of a lot of examples of adjoint functors. Okay, let's go on and see another one. Okay, so remember from chapter 3 we talked about products. So here's just to remind you. You have an object A, you have an object B. You can talk about the product of A and B. Okay, and there's projection functions like that. And what's the universal property of A cross B? It says if there's a map C from C to A, and there's another map, I think we call this K1 or KA, and there's another map from C to B, then there's a unique map like this, making sure that these commute. Okay, great. Now, what I want to do is I want to think of the product as a functor, okay? And basically it takes two objects of a category A, so this is all taking place in the category A, and it outputs an object in the category of A. So A comma B go to A cross B. Okay, great. Question, can we write this as adjoint functors? And the answer is yes, we can. So what are we saying? We're saying for any map from C to A and any map from C to B. So let's write this out. Instead of talking about two different maps, I want to talk about them in the same category. So I'm going to talk about the category of A cross A. Okay, this is pairs of objects in A, pairs of morphisms in A. And now I want to talk about this. C comma C. Here's a typical object in here. Okay, and now I'm going to talk about another typical object in there, namely A comma B. Okay. Okay, and now what does this say? What is this Ham set? Well, it's the set of all pairs of morphisms. One pair goes from C to A, one pair goes from C to B. Very nice. Okay, and what do we say? We say that this is equivalent to a morphism in A from C to A cross B. C to A cross B. Okay, that's what the universal property of a product is. Okay, okay, that's the universal property of a product. Okay, but it has to satisfy a certain requirement, namely, this commutes with this. This is a projection. This is a projection. Projection on A, projection on B. Okay, that commuting, those squares commuting, corresponds to naturality here. Don't want to get into that. What I do want to do is, instead of talking about delta of C cross C, I'm going to call it delta of C. Okay, you'll see why in a second. And instead of calling this A cross B, I'm going to call this prod of A comma B. Okay, and what I just showed is that this function, this functor, okay, has a left adjunct. Okay, so let's write it up very, very nicely. Okay, and it goes as follows. It goes oops. Okay, this is called the diagonal functor. Takes every element A to A cross A. So takes a typical element C in here to C comma C. Okay, turns out that this is a left adjoint to prod. Okay, now let's say I talked about coproducts. Well, I would have to change around this whole thing, swap all the arrows, etc., etc. Okay, well, turns out also there would be some universal property about pairs of maps to C. Okay, and turns out like this: coprod. Coprod is a functor that takes pairs of elements in here to an element in here, assuming these categories have coproducts. Okay, so here's so this functor has both a left adjoint and a right adjoint. Okay, I would like to show you what the co-unit is, what the unit is for this. Again, for every time you see an adjunction, you have to write out the Ham sets. You also have to try to look at you have to look at both the unit and the co-unit and see if it says something interesting. Okay, so let's just look at the unit here. The unit for a typical element A goes from A to what? To prod of delta of A. Okay, let's see what delta of A is. Delta of A is A comma A. Prod of A comma A is A cross A. So basically, oops, I shouldn't have drawn that. Okay, that's getting into the universal property of the co-unit. Basically, it's a morphism from A to A. Well, we call that the diagonal. We dealt a lot with that in chapter 3. Okay, so the diagonal map, okay, by the way, definitely overload. This is the diagonal map in the category of categories. This is a diagonal map in a category, within one category, within the category of A. Okay, great. Okay, so that's nice. Again, that's just more showing that the universal properties that we met in chapter 3, structures within a category, okay, can be seen as special instances of adjoint functors. Okay, next. Free forgetful. adjunctions. Okay, just like there are a lot of types of functors, so too there are a lot of types of adjunctions. Okay, and we're going to see a lot of types of adjunctions, but what we're going to do today is, what we're going to do now is we're going to focus on one of them, and we're going to build up a lot on it. Okay, and it's an important adjunction. It's about the relationship between monoids and sets. Let's just remember what a monoid is. A monoid is a set with a single operation. It's associative, and it has a unit. Okay. And this book is called Monoidal Categories, so there's a lot of, it's going to show up a lot. So let's go through this. You have a functor from monoid to set. And it's called the forgetful functor. We talked about this. Okay, basically, this takes M, a monoid, an operation, a unit, okay, and forgets to just M. Okay, that's the easiest thing. So you forget that other structure. You forget the other structure, you just think of it as a set. By the way, you can have a monoid homomorphism, and that forgets into a regular set homomorphism. Great. Now I want to talk about a more interesting functor. It's called the free functor, and it goes the other way. Sets goes to monoid. Okay, and what does this do? It takes a single set and looks at the free monoid over that. So let's just pick out a typical set, A, B, C, that's a typical set. The free monoid over that is all words or all strings, including the empty string, with these letters. So let's just go through this. Okay, so it could have the empty word. Sometimes it's written like that, sometimes it's written like that, sometimes it's written like that. Okay, it has the letter A, that's a string in this letter. It has the letter B, it has the letter C, it has the letter AB, it has the letter AA, it has the letter AC, it has B, A, B, 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 C, and it has A, dot, dot, dot. It's an infinite set, so I'm not going to go through it. Well, I'm not going to go through it in a finite amount of time, but it's an infinite set. Of course, the order doesn't matter. So that's the set of the free monoid. What's the operation? Operation is concatenation. Okay, let's remember what concatenation of two strings is. Take one string, which is basically a string of letters of A's, B's, and C's. Take another string, concatenate them, put them together, and you have a longer string of A's, B's, and C's. Okay, and finally the unit is the empty word. Okay, the empty word. And the idea is as follows: take any string of letters, concatenate it with the empty word, you get the same string of letters. Nothing changed. Okay, great. Now, claim. This is the left adjoint of that. Let's go through that. What does that mean? Okay, so what does that mean? And again, we're going to see such free forgetful functions all the time. Okay, let's just go through it. A forgetful function is something that loses structure. You forget structure. You don't think about structure. You strip it away. Okay, and the free one is one where you have all the structure possible, from the thing with less structure to the thing with more structure. Okay, so let's show how this is a left adjoint. So we're going to have as follows: hom of monoid, okay, of f of s, comma, m, hom of set of s, comma, u of m. So S is a set, M is a monoid. Okay, and now I want to do both ways here. So I want to do as follows. Let's say I want to show you how these two sets are isomorphic. So let's say you have a typical function here from f of s to m. Oops. capital M. Okay. I'm going to give you another function, g prime, which goes from S to U of M. Okay. So given this, we're going to get this. Okay, and of course we have to show that these are isomorphic, means given this, you get this, go back again, you get the same thing. So how should this be defined? So let's say I have g prime of little s. So S, capital S is a set, little s is an element of that set. Okay, well, it's going to be equal to one of the elements in here is little s. Okay, S is script S is a typical element here. So the string of length 1, which is equal to that, is which of length 1, which has one character in it. Okay, that's that. So we just do it as follows. That's just g of little s. In other words, you already told me what all the elements, including the single elements, go there. So that takes care of this. Okay, now let's go the other way. Let's say I give you a function from s to u of m. Okay, that's in here. Okay, I want to show you what you get here. You're going to get an f prime, and it's going to go from f of s to m. Okay. Oh, how is this defined? Given this function, how are you going to define this function? This function, right? Well, this is a monoid homomorphism. So we have to do as follows. F prime of, here's a typical element in here, S1, comma, S2, comma, comma, Sn. That's a typical element in here. Okay, I'd like to know what it's equal to in terms of m. Anyways, answer, this function tells me where to take individual elements of S. So use this function to define this. So this is going to equal to, you ready? F of little s1 dot times, okay, so here little f of s1 is a member of the underlying monoid. Okay, f of little s2 dot f of little sn. Okay, each one of these is a member of each one of these is an element of u of m, but multiply them out and you get that. Okay, great. Now, I don't have to only be able to go from this set to this set and back. I have to show that those two ways of doing it are isomorphic. So what I have to do is start with something here, move it to there, go back there, and it should give me back the identity. Same thing here. Start with something here, use this map to get there, and go back, and you get the identity. It's done in the book and very clear. Okay. Great. Okay. Want to look at the typical unit of this. So a typical unit, so the unit on a typical element S goes from here to u of f of s. Okay, let's think about this. F of s is the monoid of strings on the elements of s. U of f of s is the forgetful functor, and so you have a set to all its things. What is that set? So it goes as follows. So again, pick a typical element here. Where does it go to? And the answer is very simple. This goes to, on a typical element S, it goes to the string with one element, S. I don't think I should have that curly brackets. So, think of this. Oh, I'm sorry, it is maybe. No. Okay. Think of this as, here you're thinking of it as an object in your alphabet, and here you're thinking of it as a string in your alphabet. So that's pretty simple. Okay, and again, you have to look at the co-unit, etc., etc. Great. I want to now do something very special, which again will show up over and over and over. Again, this book is called Monoidal Category Theory. Monoids are going to be central to it. Okay, and so we're going to see lots of different ideas here. Great. I don't want to look at an arbitrary category S. Instead, I want to look at a special, I don't want to look at an arbitrary set S. I want to look at a one-element set called star. Okay. Okay, so that is a one-element set. Okay, so let's look at what the alphabet looks like. Think of star as an alphabet. I'd like to see what the words look like. Anyways, very simple. The words, so F of star is equal to, well, I have to tell you what the words are. Star, this is the empty word, or star, or a concatenation of star and star, or a concatenation of star and star and star, or dot, dot, dot. Goes forever. My friends, we have just invented the natural numbers. Okay, so what's the natural numbers? It's the free monoid. It's the free monoid on one object. Great. What's the operation on this monoid? Concatenate. So if I have a string of 8 stars and I have a string of 5 stars and I bring them together, I get a string of 13 stars. Very nice. Addition. We've just invented addition. Okay, this is the empty word, so it doesn't contribute anything. Okay, but, so that's what this is. Okay, great. Now, I want to write down, by the way, hold on before this. So that takes care of that. We'll see what this does in a second, but let's go through this. Here's in the category of set, you have a one-object category, and a one-object set, and you have a forgetful functor from the monoid. Well, what does this do? Very simple. This is a set. There's no restrictions on what type of functions there are, function homomorphisms. So a map from here to here basically picks out an element in this set. Okay? We saw this in chapter 1. A map from a one-object category to a set picks out an element. Great. Okay, so now I want to see how this works, how this adjunction works. I'd like to look at it from the universal property. I'd like to look at it from the unit of the thing. So here's the unit. Here's what the unit says. That's the one object set. This is U of F of the one object set. Okay, let's go through that. This is a one object set. F of it is the natural numbers. U of F, thought of as a monoid, U of F is just the set of natural numbers. Okay, now what do we want? We want to write the universal property of it. The universal property says as follows. This whole morphism, this whole diagram is happening in set. Okay, and so what this is, okay, what this says is for every star, for the one object category, for every map from here to here, which means from the one object set to here, which means you're picking out a typical element here. So this star is going to go to a typical element here. That's a small m. Great. Now, again, we have to write what the universal property is. What it says is that there's going to be a map from f of star. Hey, we have a better name for f of star. We're going to call that the natural numbers to m. Okay. We're going to call that sorry, we're going to call this F, we're going to call this F prime. Okay, well, if you take F prime and you do U of it, so you're going to get U of F prime, okay, then what are you doing? Okay, hold on one second. This map is very important. This is in set. This is in monoids. Okay. Now watch what this category is doing. What this function is doing. What any function from the natural numbers to n is. So it's going to send 0 to 0 here. The identity here. Very good. It's going to send 1 to some element here. It's going to send 2. That's another way of saying 2. 2 is star star. Well, it's got to preserve the monoid thing. So it's going to send it to little mm. Little mm. Okay. So here's the image of F prime. It's the unit m, mm, mmm, dot, 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 dot. That's what the image of F prime is. Basically, the natural numbers is going to pick out elements over and over and over and over again. The same element over and over and over and multiply it into this thing. Okay, and great. And what that means is this is going to happen. So, for example, the number 6 is going to go here to m. We'll write it m to the 6th. Okay, so the one object is going to go here, and that's going to include in here, and so we're going to get that. Okay, great. I want to keep this in mind, and I want to write what F star is really. I want to write it in 3 different ways. And again, it's a little bit overkill in terms of monoids, but what we're going to do in chapter 6, 7, chapter 5, 6, 7 is we're going to show how this works with not monoids. Monoids are very simple things. They're just sets with extra structure. We're going to talk about monoidal categories, which are categories with extra structure. So we're going to need some of the ideas from here for that. Okay, so let's write it out very carefully. Okay, and it goes as follows. So I just want to write this like this. Properties of F of... Sorry. It's an amazing thing. What we're doing here is an amazing thing. Where we just took a one element set and we got a lot of properties out of it because we're not looking at it as a one element set. We're looking at it within the image of the free. So this is the free monoid. Okay, so let me just tell you what 3 different ways of describing F of the one object set. F of the one object set is, English, is the free monoid on one object. Okay, let's write it another way. Okay, for every m in M, there, by the way, M is a monoid, M is an object of the monoid, there is a unique morphism. Okay, this is this triangle that I drew down here a second ago. F from, maybe I called it F prime, to M, such that F, that's this little f, of star, that's the typical, that's the generator of this, is equal to m. That's a small m. So for every m, there is such a function that pulls out that element. Okay? Okay, and a third way is as follows, just writing it the Hom set definition. Hom of monoids, okay, of F of star, comma, capital M is isomorphic to HOM of sets of one object set, comma, M. Sorry, that shouldn't be M, that should be U of M. Okay, now what do you call all the maps from a one object set to U of M? Okay, and the answer is this is a set thing, so this star can go to any element there, and so this is isomorphic to U of M, the set U of M. Okay, so again, that's just another way of saying it's the free monoid on one morphism. But again, we're going to see all three of these much later on in chapter 5, not much later on, in chapter 5, 6, and 7, to describe monoidal categories and variations of monoidal categories, more complicated monoidal categories. So these free things, let's say that, the free blanks over a one object blank is very important. Shows up a lot. Okay. Okay. Great. Continuing on our long thing of lots and lots of examples of monoidal categories, let's talk about this. Okay. So what I'm going to describe is a family of adjunctions. Lots of different types of adjunctions. One has to do with categories, one has to do with graphs, one has to do with topological spaces. Okay, and so we're going to talk about all three of these, but we're going to concentrate on this. Basically, all three of these are as follows. They're sets with extra structure. Okay, so you have here, you're talking about what's a category? It's a set of objects with other structures, namely morphisms. What's a graph? Well, it's a set of vertices or nodes, or whatever the hell you want to call it, with a bunch of edges in between them. What's this? What's a topology? Well, a topology is a set of points, and you have the open sets to tell you what's connected to what, what's near what, and what's not near what. Okay? So all three, so you're going to see in 5 minutes that all three of these have the same type of adjunctions, but we're going to focus on our favorite subject categories. Okay, so let's do that. Okay, so I want to describe 4 functors from between cat and set. Okay, so let's do them. One is our very lovely forgetful functor. We love forgetful functors. Okay, so this goes from cat to set. Okay, and basically what it does is it takes a category, any category, forgets all the morphisms before it. So imagine, this is before I met you, imagine you're in the middle of chapter 1, okay, we didn't have morphisms, so you only have a set of objects. Again, the category need not be finite, and therefore the morphisms need not be finite. Okay, so this is a forgetful functor. It takes a category, which is objects and morphisms, forgets the morphisms, and just gets the objects. So we've seen this before. Let's talk about this. Here's another functor. It goes from set to cat. We actually saw this before also. What does this do? It takes a typical set, and D of S is going to be a category. What are the morphisms? There's only trivial identity morphisms. So it's the smallest thing that makes this work, namely identity morphisms. That's it. That's the only morphisms you're adding in. There's no objects, there's no morphisms between two different objects. Okay, great. Another thing that I do not think we saw is, also from set to cat, okay, but this is something a little bit stranger, okay? So let's take this. Typical set S is ABC, okay? I want to show you what the C for continuous, D for discrete, C for continuous. It's going to be the following category. It's going to have 3 objects, Okay, and there's going to be identity morphisms, of course. Every category has identity morphisms. Okay, and there's going to be a unique morphism between any two objects, either way. So there's a unique morphism from A to B, there's a unique morphism from B to A, C, etc., etc. Turns out all these are isomorphisms, because if you go this way and then this way, you get to the unique identity. So it gets nothing. Okay, so let's think about this. This is the discrete of S here is just a category with just objects. No morphisms except the identity. So if you want, you could think of this. This is A, this is B, this is C. So this is like this, identity morphism, identity morphism, and identity morphism, but nothing in between them. Here we have something in between them, one morphism between them. Okay. Okay, and finally, something we have not seen before, and that goes from cat to set. Okay, and this has a name. Okay, pi 0 is the set of components of cat. Let me explain to you what that is. So, take a typical morphism in a category. So you have a category A, and you have a morphism in that. Okay. Well, these two are going to be related. Okay. And if you have another thing, let's say B and B prime, they're related. Okay. Okay. But as long as you don't have anything connecting them, they are separate components. So this will be one component, and this will be another component. So two objects are considered in the same component if there's a morphism from one to the other. Okay, great. So pi 0 of A is the set of components that you have. So the way to think of this is as follows. You have a category, and categories are all, there's arrows in between a lot of the things. And if you can reach from one category to the other category, you shrink that whole thing that you can reach to one point or one component. And there's another component, and there's another component, and there's another component. You shrink things to their components. Okay, great. You have these four functors. Let me show you how these four functors relate to each other, and we can only do this with adjoint functors. Okay, and so we have the following. You have the category of categories. You have the category of sets. Okay, there's a forgetful functor like this. There's a functor like this called C. There's a functor like this called D, and there's a functor like this called pi 0. Okay, and now there's not one adjunction, there's not two adjunctions, there's three adjunctions. Okay, now in the book I go through showing how each of these are, for each one of these adjunctions, I have to show how the Ham sets work out. So it works out very nicely with the Ham sets. But besides that, I also go through every single one of the units and the co-units. For each one of these adjunctions, there's three adjunctions. There's a unit and a co-unit you have to go through. I just want to go through one of the co-units for this adjunction. I'm sorry, yes, this is the co-unit. So it goes as follows. Here's a typical category, A. Okay, and the co-unit is going to be as follows. D of U of A to A. Okay, let's go through this. U is a category. A is a category. U of A is the set of objects in the category. D of U of A is the set of objects, okay, with just the identity morphisms. Okay, and how does that relate with that? So in other words, what you want to do is you want to think of a category, let's say something like this. Okay, then U of A erases the morphisms. D of A now thinks of this as a category with just, A is a category. It has identity morphisms and some other morphisms. Okay, So let's write it like this. Identity morphisms and some other morphisms. Okay. This is a little bit silly because if it has this and this, it has to be this. So let's do it like this. Okay, now forget that it's a category and just think of it as a set. So now we have the set of objects. Now take the free set of objects. Okay, so that adds in just identity maps. And this inclusion is the inclusion of the objects and the morphisms, and the identity morphisms into the original thing. So here's the way to think of it. Take A as a category, strip away the excess morphisms, include it into A. That's the co-unit of this adjunction. Okay, very nice. Very nice. So this works with categories. Okay, and it's a very nice adjunction. It's adjunctions, 3 adjunctions. Okay, but you know what? It also works for graphs. Okay, and again, I'm going to be a little bit quick here. The book goes through all the details, but for any for any graph, you can forget the morphisms, you can forget the edges of the graph, you get to that. So this is very similar to what we saw before. For any set, you could talk about the continuous graph on it. Basically, that's a graph, not a category, a graph with exactly one object between every 2 morphisms. This, for every set, you can just think of a set as a discrete graph. There's no morphisms between the vertices. It's just a bunch of dots, nothing else. No even identity cells. Okay, and this goes the other way around. Okay, namely, for every graph, you can go to sets by using the components. So again, take a graph, and here I'm not going to talk about reachability. I'm just going to say, well, actually you do talk about reachability. I'm just going to say 2 objects are in the same component if there's a morphism from one to the other. Okay, and so you get that. Okay, okay. I just want to do something now. There's also from cat. This is not in the book. Pi 0, discrete, continuous. Okay. In categories, you can forget that you're dealing with a category and you get a similar type of thing. Okay, we'll actually deal with this in a second. You can compose these, and again, this is composition of forgetful functors. So here you have a category, you can forget the composition. You get just a graph. You forget the identity morphisms and the composition. You have a graph, you can forget the morphisms altogether. You can compose these 2 functors, and you start off with the category, and you just get the set of objects in the category. Okay. Similarly here, you can go like this. Components. By the way, this is almost the same. Oh. Well, I don't know what that is, but anyways, that's very nice. Okay, hold on, we're not finished. I said that this thing with categories, you can change it for graphs, but you can also change it for something else, another another structure that's based on set, which we call top. Okay, and there's similar adjunctions. Now, if you studied topology, you would see this first and then came to category theory, but we are category theorists, we studied categories, so we could think of this as a variation of what we just saw. Let's just go through this. Take a typical set, you can look at the continuous topology. I think that means with all possible open sets. In other words, the topology is the power set. Take a topological space, you can forget its topology and just look at the elements of the set. Take a set, you can just put in the empty set and the whole set, and that's your topology. Not a lot of things are connections. And then here's where it really shows up, the pi 0. You have a topological space, which can consist of a lot of different parts, non-overlapping parts. And so the pi 0 of this topological space is just going to be 1, 2, 3, 4, 5 dots, corresponding to 5 components. 1, 2, 3, 4, 5. Okay? Okay, so, and again, for all of these, in top, in graph, in cat, you have to go through the Helm sets, see that it works out. You have to go through the units, you have to go through the co-units, see what they correspond to. Okay. Okay, now I want to focus on I want to focus on graph cat is a forgetful functor. Okay, it has a left adjoint. Okay, and I did this as D, but I want to call this L for the left adjoint to that. Okay, and basically, what's a category? It's going to have the same objects as this. So I want to know, here's a typical element, G, in graph. I want to look at what L of G looks like. Okay. Okay, so here's the object, and this is a category, L of G. I want to look at what it is. Okay, and the answer is, it has the same objects as G. But we have new things. L of G has new things. First of all, it has identity morphisms. So we better make sure we have identity morphisms in there. So take the objects and add in identity morphisms, little loops on those things. If they didn't have one already, put them in. Okay. Next, what else does a category have? Answer, composition. So we have to be able to compose those. Okay. So if there's a dot here and a dot here and a dot here, and there's an edge from here to here in this graph, then in this category, we're not only going to add in identity morphisms, but since there's a dot here and a dot here, we have to be able to add in that. So what this is the free category above a graph. You add in all possible things to make this LG into a category. So you have to be able to add in identity morphisms, and you have to be able to add in compositions. Okay, I want to show you two special cases of this. Okay, two special cases of this. One is a stupid category, a stupid graph with just one object. Well, the category that corresponds to that is 1, which is a category with an identity morphism. I'm sorry, a category with one object and identity morphism. So that takes care of that. That's a pretty stupid. So the free category over the one object graph is the one object category. We keep the same objects, we just add in enough morphisms to get it, to make it into a category. Great. Now let's change this. Let's say I have one morphism in this category, and the one morphism goes like that. Okay. Now, that morphism is not an identity morphism, because there's no such thing as an identity morphism in the category of graphs, because there's no composition. So you have no object, you have no things here. Okay, what's going to correspond to this, the L of this category? And the answer is, well, it's going to have one object as before. It's going to have an identity morphism as before, not as before, as before. Okay, but this morphism now has, we can do this, it's going to have this morphism also. So we'll call this, I don't know what to call it. Okay, but now you can also take this morphism and compose it with itself. Okay, and you get that. And you can compose it with itself again, and you can compose it with yourself again, and you can compose it with itself again. Okay, and you might want to call this 0, 1, 2, 3, 4, 5, dot, dot, dot. Okay, so let's say this again. That's basically the natural numbers. That's basically the natural numbers. So let's say it. The free category of the graph with one object and one extra morphism is the natural numbers. Okay, and so this concept of composition is very important in category theory, but it gives us these natural numbers. Okay. Okay, let's look at some more examples. Okay, so we'll have more examples, but I just want to go through some properties of it. So one of the things we said was, I don't know, identity, okay, and this is right composed L. This is, okay, one of the things we said was, we started off talking about when this is equal, then we changed it to when they're isomorphic, okay? So this was originally equal, then changed it to isomorphic, and then we weakened it to just a morphism, okay? Okay, so, and we said as follows, this morphism has to satisfy these triangle identities. So that's what an adjunction is. It's a weakening of equivalence, whereas isomorphism is when they're equal, equivalence is when they're isomorphic. Here we have where they're not isomorphic, there's just a morphism between them. So let's think of it another way, is equivalence is a special case of an adjunction. An equivalence is a special case of an adjunction, where the co-units and units are not only a morphism, but an isomorphism. So that's the way to think of it. But there's something a little bit off in what I'm saying, because when we talked about equivalence, we never talked about those triangle identities. Okay, so how could I say that an equivalence is a special case of an adjunction? All adjunctions satisfy this triangle identity, and I never mentioned a word about the triangle identities when we talked about equivalence. Okay, so we have a problem, and I want to explain to you why it's not a problem. Okay, and the idea is as follows. Let's just make a Venn diagram, so we can call these adjunctions. Okay, so these are morphism this way, morphism that way, such that these triangle identities are satisfied. Okay, then we can have equivalences. And this is morphism this way, such that the composition is isomorphic to the identities. Okay, now I'm going to make a new thing called an adjoint, an adjoint equivalence. That's a new definition. Okay, what's that? Their equivalence, that means compositions are, the units and co-units are isomorphisms. However, they also satisfy the triangle identities. Okay, so they are both adjunctions and equivalence. Okay, okay. By the way, there's a special subset of these where they're isomorphisms. Okay, so now here we can see all of what we saw in the beginning of chapter 4. Chapter 4 is about relating categories. Section 4.1 is about functors. 4.2 is, I don't know, equivalences, and 4.4 is adjunctions, but now we can see them as that. So there are a special type of equivalences, which are called adjoint equivalences, which not only have the unit and co-unit to be isomorphic, but they also satisfy this triangle identity. Great. Now, how does that help us? Okay, the following theorem helps us. Theorem. Every equivalence can be turned into an adjoint equivalence. So it's wrong to say an equivalence is a special type of an adjunct, as an adjoint. An adjoint equivalence is a special type of adjoint. Okay, but every one of these guys can be turned into one of these guys. Okay, and I do it in the book. It's not a complicated proof. What you do is you take an equivalence and you nudge either the unit or the co-unit such that it satisfies the equivalence, such that it satisfies the triangle identities. And the idea is as follows: it's almost there. It just has to move it. And what you have to do is you have to measure how far the triangle identities are from being satisfied, and then you change your units and co-units so that they do satisfy it. So it's not hard. It's just technical, and I don't want to get into it. And again, it's not really there to satisfy it. Whenever you think of an equivalence, you might as well think of it as an adjoint equivalence. Okay, that takes care of that. Okay, now something really nice. Again, these are more properties about adjunctions. It shows up all over. You have a left and right, and we write that like that. Okay, great. So let's just remember what this is. This is an adjunction where units and co-units are morphisms, nothing more than just morphisms. They happen to satisfy the triangle identity. Very nice. Well, you know what? Let's say I start here, I go around here, and I come back, and I get something that's isomorphic to this. Well, in that case, the unit and the unit, or the co-unit, whatever, is an isomorphism. So it turns out that for every adjunction, for every single adjunction, there is we can look at a subcategory of A where the objects are, we can look at a subcategory of A where the objects satisfy the following property. If you go this way and you go this way, you get to something isomorphic to the identity. So you get the same thing here. If you start here and you go here, you get something isomorphic to what you started with. Okay, so here, turns out that this, we're going to say this, R, the restriction of R, not all of R, because this is a subcategory, okay? And same thing here, L, the restriction of L, okay? Now, this is an adjunction. This is going to be an equivalence of categories. Okay, and now here what we say is the units and co-units are isomorphisms. Okay, so let's put it another way. Every adjunction has inside of it a subcategory that's an equivalence. By the way, it could be the subcategory is the empty category, but that's okay. In other words, nothing matches up exactly, but that's okay. Okay, but still the statement stands. Now, maybe I shouldn't do this as a... Okay, let's do it as that. We'll say it is a skeletal category. And the skeletal category of B, okay, also has maps like this and like this. We'll call this L hat, and we'll call this R hat, okay? And here, it's not an equivalence of categories. Here's an adjunction, here's an equivalence. This is an isomorphism of categories, okay? There's an isomorphism. So within, we saw this before, within every equivalence, built inside is an isomorphism, and these are really strict. And you can see this from this point of view. The units and co-units are identity morphisms. In other words, go back and forth and you get back not to something isomorphic, but exactly equal to where you started from. Okay, so this is a nice summary of all the different structures, the different levels of structures you can have. You can have an equivalent, you can have an adjunction, you know, a subcategory of that is going to be an equivalence, and a subcategory of that is going to be an isomorphism. In some sense, this is really the skeleton of this relationship. And again, this could be empty, but that's a nice way of thinking about this. Okay, great. Next. Again, properties of adjunctions. So guess what? Adjunctions compose nicely. We're always looking at how things compose. So let's do this. This is L, this is R, this is L prime, this is R prime, this is a left adjoint, that's a left adjoint. Okay, now let me say, but not, let's say, the composition of left adjoints is a left adjoint. Okay, and you can make the same statement about right adjoints. The composition of right adjoints is a right adjoint. Okay, now there's a few parts of this, a little technical, but basically I have to do this. Now this was a mistake in the book. There's typos in the book, but basically it goes as follows. You're in the category of C, so that's over here. Okay, and you have L prime. Sorry, L prime L of little a. So here's little a, L prime, you're in C. Okay, and you have little c over there. Well, from the fact that this is an adjunction, so then we get in B of, let's leave out this L prime, we have L of A, okay, and this L prime is adjunct with R prime, so we're going to have R prime of little c. Okay, that's a typical element in B, so that's in there. Okay, and this is of A of what? Little a, comma. Now here, notice what I'm doing. I'm going to get rid of this L. By using this adjunction, I'm going to get rid of this L and put another R over here. So this is going to be R prime of C. Okay? Again, we have to show naturality, we have to et cetera, et cetera, et cetera. There's a lot more pieces, but that's basically showing that. Okay? So the composition of left adjoints is left adjoints. The composition of right adjoints is right adjoints. Okay. Great. Question. When we talked about isomorphism of category, what we had was the inverse was unique. Okay. When we talked about equivalence of categories, you have a functor from one to the other and you have an equivalence. Well, it's not unique, but they're unique up to an isomorphism. Okay. By maybe even a unique, but okay. But now we're going to talk about adjunctions, and it goes as follows. Theorem: a right adjoint is unique up to a unique isomorphism. Of functors. Okay, let me explain to you what that means. That means if R is a right adjoint to L, and R prime is a right adjunct to L. So you have two different right adjuncts to L. Now again, when you have an isomorphism, you'd say R and R prime are really the same. You don't have, there's only one inverse. Well, here it's not true. They could be two different things. They are isomorphic. I'm sorry, that's an equivalence of categories. They're iso, okay, but uniquely. There's a unique isomorphism in between them. So that, again, that shows, we talked about this before, we're obsessed with this notion of uniqueness, okay? To what extent is there only one? Okay, so there's a unique isomorphism. Now, we've seen this idea before, okay? Namely, an initial object is unique up to unique isomorphism. A product, a limit, is unique up to unique isomorphism. So this is we're going to see this over and over again. And by the way, we'll see how this is actually related to this notion that a limit is unique up to unique isomorphism. It is very much the same type of idea. Okay, a special type of adjunctions that show up a lot, two special types of adjunctions that show up a lot. You have a category A, and it includes into B. Okay, well, if this inclusion has a left adjunct, so this is the inclusion. If the inclusion has a left adjunct, so not only is this a subcategory, but it's called a reflective subcategory. Okay. Furthermore, if A includes into B and it has a right adjunct, okay, so then we call it a co-reflective subcategory. Okay. And we like such things. They are a subcategory, but they share certain properties. They share some very nice properties with that. Okay, one final example, and we'll call it a day. Okay, and this is just the same type of example as we saw with the free monoid. Okay, the free and forgetful monoid, but this shows up so often that we have to actually point it out. Okay, so it goes as follows. You have K vector spaces, okay, and you have sets. Okay, so instead of talking about monoids and sets, we're going to talk about K vector spaces and sets. Okay, there's a forgetful functor like that. Take any vector space. What's a vector space? It's got objects which you can add and scale and multiply. Okay, well, you can forget the addition and you can forget the scale and multiplication. You just have the set of vectors. Okay, the set of objects. Guess what? There's a free thing that does that. Goes the other way. Take a set, you get a bunch of vector spaces, a bunch of things. Now, when we dealt with monoids, the objects were basically strings of objects because there was one operation you had to do, namely composition. Okay, so there was one operation. But here we're going to deal with vector spaces, and there's two operations, and we have to worry about those two operations. So I'd like to tell you what f of s is. Okay, so let's say s is equal to, don't move, what do I want to do? Oh, s is equal to S1, S2, Sn, okay? I'll tell you what these things are, though. They should be called basis elements, but that's fine. Okay, f of s is the set of all things where you can add these and scalar multiplies. So here's a typical element in here. K1, S1, that's scalar multiplication, plus K2, S2, plus, plus Kn, Sn. That's a typical element in this free set. So you've added in the scalar multiplications, and you've added in the ability to add them all together. This is a typical element. Now, once you have such a typical element, okay, you can take two such typical elements, you can add them together. You can take two such typical elements, you can scale and multiply them together. So that gives you this. Okay, so that's very, very nice. Okay, and this is a left adjoint to this. Okay, one caveat, which is very interesting. There's a subcategory of this called fin set. There's a subcategory of this called fin set, finite sets. Okay, and you have K finite dimensional vector spaces. Okay, and guess what? There's a free functor like that. Okay, so if I take a finite basis, if I start off with a finite set, and I just can build up a finite dimensional vector spaces like that. Okay, and I showed you how to do it. Take all the elements of the basis, that set S, and you put in all the scalar multiplications, all the additions, and you get a finite dimensional vector space. This is a subcategory of this. Okay. However, there's something missing here. This functor does not exist. Not it doesn't exist. This forgetful functor, restriction of this is not. Because take a finite dimensional vector space, you don't necessarily get a finite set. If you forget the multiplication, a finite dimensional vector space is still an infinite dimensional thing because K is an infinite dimensional thing. Okay? By the way, if K is a very, very nice field, that's very, very small and equals to that, then this does exist. Okay, and basically you have your strings are strings of zeros and ones. Anyways, it's very, very nice. But in general, K is complex numbers or the real numbers, and this is not really true. Okay, so you have this adjunction, and you have this functor, which is a restriction of this F. Okay, this shows up over and over and over, and so it shows up so often that we have to actually state it. Okay, so let's see what we did. So we talked about adjunction, and I told you adjunctions show up all over. It's the way of describing universal properties. Adjunctions are the way of describing universal properties, and they show up all over. They're very, very important. It's very, very important to go through the chapter and do all the exercises and work out every time you see an adjunction. Work out the Ham sets, work out the units, work out the co-units, and you'll see some very interesting things. Okay, now we're going to use adjunctions basically for the rest of this chapter. I mean, basically, I stopped here from examples, but section 4.5, 4.6, 4.7, 4.8 are all using these adjunctions for everything. And the rest of the book is also full of adjunctions. So you really have to wrap your head around it and get it. It takes time. It takes time, and it takes a lot of examples to go through. So try to do the exercises, etc. Have a wonderful day.